I don't mind about to record, so just go on. Thank you for organizing this seminar and also having me here. Today, I'm going to briefly talk about my work on the estimation of time series models using the empirical distribution of residuals. So in this paper, we propose a new methodology, estimation methodology for estimating a general linear time series model, which is robust to non-invertibility and non-causality. So before I start, let's talk about the motivation. So generally, when we talk about, or normally when we talk about a linear time series, we define it by a moving average representation. And these phi's are the ones that we want to identify and estimate. And the innovations are either ID or white noise or martingale difference sequence. So usually we define it in a way with just one-sided moving average representation, which normally confine the analysis into class like causal and invertible time series. And as regarding the identification or estimation of the parameters of interest, then we just need to use the second order moments-based methods like OLS or Gaussian maximum likelihood estimation. But what if we try to expand the class of linear time series models? So we just allow this moving average representation to be two-sided in the sense that this J is from minus infinite to the positive infinite. And in the sense we can incorporate non-causality and non-invertibility into this nonlinear time series, which allows for temporal dependence in both future, present, and the past. So that means like in the ARMA model, we don't restrict the location of the roots of both polynomials as long as they're away from unit. So they can be larger than, greater than one, or they can be smaller than one. So why do we care about this type of process? So there are a bunch of literature about non-invertible process, which actually these takes place in the moving average part. So Lippi and Ridgely, very early, they have found out that this type of process can be used to generate different types of impulse response functions, which also make sense economically. So they cannot be excluded naturally, and also it can be used to generate information or characterize different information flow with unusual discounting pattern due to the fiscal foresight of the tax policy. Also, besides, it can also serve as a solution to non-revealing equilibrium with heterogeneous agents, which means if the economic agents, they have private informations, the equilibrium could be non-invertible in the sense. Also, if this happens in the autoregressive part, then that means it's called non-causal process. And usually this type of process is used to generate nonlinear dynamics like local explosiveness, symmetric cycles, or volatility clustering. Also, it has been shown that this can be used to improve forecasting accuracy in macroeconomics and finance. And also it can be work as an alternative to non-invertible process in modeling forward-looking behaviors of economic agents, like the one that we just introduced, non-invertible moving average process. So if we stick to the original conventional estimation technique, which is OLS or Gaussian maximum likelihood estimation, we are unable to identify non-causality and non-invertible under non-Gaussian, which they always give us the causal and invertible solution. So that is telling us that we need to exploit more information beyond the second order moments from the non-Gaussian ID model innovations. So there are, in the current literature, so there are two types of estimation for this type of process. One is called a one-step, and one is one-step. So you can just use non-Gaussian maximum likelihood estimation. But with this approach, you either need to assume that you already know the density function, which is quite strict, or there are some distributional assumptions on the density function that you need to satisfy. Another one is minimum distance estimation. So literally, they exploit more information from higher order moments beyond the second order moments, like the third order moments or fourth order moments, in both frequency domain or time domain. Also, Velasco has proposed another methodology based on a dependence measure using characteristic functions, which can be used to capture all pairwise dependence in the residuals. And another one which is involves two steps in the estimation. So first, we fit the model with fit the data with a causal invertible model, but the residuals is not gonna be ID. It's gonna be white noise, but dependent. And then second step will be based on these residual that we get from the first step. We propose another methodology, especially for this type of process, which is called all-pass residuals. And there are maximum likelihood estimation or rank-based estimation or least absolute deviation methodology for this specific type of process. But this is two steps. So the asymptotic properties of the estimator is not that clear because the second step is artificial. It's not based on the natural process. So in this paper, I propose a new minimum distance estimation methodology based on a dependence measure using the empirical CDF of the residuals. So with this approach, we achieve the identification of general time series models robust to non-causality and non-invertibility without prior information on the distribution of the innovation. And we just need to impose very mild conditions on higher order moments for the asymptotic analysis of the estimates. So that means like compared to the estimation method based on the higher order moments, we kind of have this kind of advantage. And also because the CDF, the cumulative distribution function, is quite flexible. So this methodology is possibly extended to different dependence structure like conditional mean independence or conditional quantile independence. So before we move on to the facial estimation part, we would like to introduce this dependence measure that we adopt in this paper. So if we have one sequence of random variables xt, then if these two variables xt and x minus j are independent, that means intuitively the joint CDF would be equal to the product of these two marginal distributions. And we just construct our general covariance based on this distance, which is the discrepancy between this joint CDF and the product of these two marginal CDF. So it equals to 0 if these two variables are independent. So this statistic has been used for testing serial dependence in several papers by many scholars. And we adopted the spectral one, which is just a Fourier transformation of the previous introduced covariance, and the distribution function would be just an integration of these density function over the frequency. So this statistic takes into account all pairwise dependence contained in this XT sequence. And if we impose ID assumption of this sequence, then the only term remain will be this self-correlation. The rest of the terms will be equal to 0 because of this IIDness. So now we try to apply this dependence measure into the residuals that we generated from the model. So the residuals can be actually calculated or recovered by this linear filter on the observations. This linear filter is generated by the inverse and of these moving average polynomials times itself, and the general spectral density and distribution of the residual sequence will be just apply the statistic that I introduced before, with replacement of this xt by the residuals that you get from the sequence, from the data. And the theta 0 is the true value of the parameter. So that means if the residual is evaluated at the true value, then the true innovation is recovered. So the model will be, if we impose idealness on the innovations, then we can simplify the spectral density and the spectral distribution into this single term, which just characterize their self-correlation. And the population loss function that we adopted in this paper is an L2 distance between the CDF and the CDF, unrestricted CDF, and the restricted one when we impose ID. So you will see that naturally we will have a weighting function on higher order lags, which you are gonna see in the asymptotic variance. So under some assumptions that I'm not going to elaborate in this because of the time. So basically, we just need to impose that the density function, some smooth conditions on the density function innovation, and that the residuals is recovered. The true innovation is only recovered when the theta is evaluated at the true parameters. So we will have these when theta is evaluated at not the true value. So we will get a sequence of residuals which do not satisfy the full or pairwise independence. So that must exist one covariance at some certain point, which is not zero. So that means the loss function is gonna be positive. And only if and only if that theta is evaluated at the true value, we will have the loss function equal to 0. So this gives us the identification without imposing further conditions on the innovations. And we don't need to restrict the location of the roots to both moving average and autoregressive polynomials within the unit circle. And the consistency follows from the theory, which we need to impose further smoothness of the innovation, of the density function of the innovation. And the innovation, the variance of this innovation should be finite. We will get this consistency. For the asymptotic normality, it is a bit tricky because we don't have the differentiability of the loss function, since we are using indicator function all the time. So in this case, we try to approximate this indicator function with a smooth the empirical CDF, which I use lambda to denote. So this lambda have to satisfy certain conditions, which is unbounded, defined on unbounded support, and is different with some differentiable probability density function away from 0. So that kind of there is no information loss in this transformation or this approximation. And this lambda function has to converge to the indicator function when the smoothing parameter h goes to 0, when t goes to infinite. Oh, don't know why this one is like this. Oh, great. So the loss function in this case will be just replaced by these by these covariance based on the smooth, the CDF. And as I argued before, this smooth approximation doesn't have any information loss. So the identification, the consistency can be easily established following the paper by Carlos Perasco in 2022. And then the asymptotic normality of this estimator for fixed edge smoothing parameter is very easy to establish because we have everything smooth. So we can just construct a derived asymptotic normality based on the score and the Hessian matrix of this proposed estimator. But the ultimate idea is to derive or to approximate the asymptotic normality of the estimator that we proposed in the beginning based on the indicator function. So we try to make this h goes to 0 at the same time when t goes to infinite. So in this time, we have to be very careful with this h, because if this h goes to 0 too fast, that means like this approximation goes to the indicator function is so good that we probably couldn't fix the problem when we used to have with the indicator function. So the convergence rate of this estimator problem is not going to be square root t, but it cannot be too slow as either, because if it goes to 0 too slow, then probably the bias of this approximation using this lambda function of lambda smooth ZDF is gonna be non-negligible, so you are going to see it in the asymptotic distribution. So we derive some rough conditions on the smoothing parameter that it has to satisfy this condition here. So basically the rate has to be between t-1 to t-1/4. So we have this condition for the smoothing parameters. And as you can see also, like this asymptotic variance has this sandwich form. So this means like there must be some information loss in this estimator. But this can be solved by using different weighting or replace the generalized spectral CDF with the density function and appropriately choosing some weighting functions. So the standard error can be computed by replacement of each component in these H0 and H1 by analogy. So in the information we try. Sorry, how many?
Just to remind you, a couple of minutes now for the simulation. It's already 5:10.
Okay, great. Thank you. So we're going to talk about, I'm going to focus on the simulation. So in the simulation, the data generation process is an AR1 with theta equals to either 0.4, 0.9 in the causal case, or the inverse in the non-causal case. And the innovation, we use uniform and the t-student and also chi-square distribution. So generally it covers a heavy tail, light tail, symmetry, and these type of innovations. And we use two approaches of choosing this weighting function, which one is empirical CDF of the residual, and the other one we try to standardize the residual and then adopt a standard normal CDF. The sample size is 100 and 200 with 100 independent replications. In the table or in the result, we report the percentage of correct root identification in both approaches. So we can see that if we compare these two approaches or two weighting schemes, we can basically see that as long as the innovation doesn't follow uniform distribution, that the standard normal CDF, this approach gives us better performance in terms of this percentage of correct identification of the roots. And also if we compare the results in the blue column and the red ones, we can tell that when the root is close to the unity, the performance is relatively worse, but it's understandable because it's very difficult to distinguish these two numbers in magnitude. And also we can see from the result that when the innovation have asymmetry or skewness or asymptosis, the performance will be better. That means that we can get further information from skewness and the kurtosis. So let's jump to the discussion. about the application. So to illustrate this methodology, we apply this estimation technique to a series of 753 daily trading volume in Microsoft stock, which is already studied by Bradit in their paper. So we find out that our methodology favors non-causal representation to these data. And with this model, we can capture volatility clustering. Apart from that, we can also capture the dependence between different percentile, which cannot be characterized by the classical AR arch models. And also, as I argued before, that this methodology can be extended to different dependence measure under like martingale difference sequence or quantile independence innovations. And we plan to do in the future, we plan to compare this methodology with other alternative ones in terms of efficiency and like Gaussian maximum likelihood or maximum likelihood estimation, assuming that distribution of the innovation is known. Also, we can actually improve efficiency by adding higher order dependence into this methodology, like triple dependence.
That's because you're taking the next presenter's
That's what I want to say.
Can you summarize in one sentence because you're taking the next presenter's time. So summarize instead of going into details now. I'm sorry.
Okay, great. So
do you have any results to show us from the empirical? No. Okay.
No, I just conclude with one sentence in the empirical application.
Okay. Thank you very much. Then